What is the source of quantum advantage? Quantum mechanics differs from classical mechanics in a way that allows for exponential speedup in certain computations that could not be repeated in a classical system. What unique property of quantum mechanics could be responsible? One property you often hear cited as the source of quantum advantage is entanglement. Another is contextuality, both of which have papers backing up this claim. Yet another is superposition, which is the one most commonly cited in popular media sources, which state that a qubit can be in two states at once, as the source of quantum advantage. Another you often hear commonly talked about is non-determinism, which is unlikely a source of the advantage. So which is it? Let's talk about quantum non-locality. Bell's theorem shows us that there is some sort of non-locality to quantum mechanics. Despite common misconception, Bell's theorem does not actually prove there are no hidden variable theories, but instead shows that there is some sort of non-locality to the universe. When it comes to entanglement, if you remove non-locality, then entanglement just becomes local correlations, which already exist in classical probability theory. It ceases to be spooky and becomes rather dull. The same is true of contextuality. If you remove non-locality, then contextuality also is something that shows up in classical probability theory. The term superposition is actually borrowed directly from classical mechanics, since it just refers to superimposing waves on top of one another. If superposition could explain quantum advantage on its own, then it could be replicated with classical waves, such as sound waves, and there would be no point in building quantum computers. As for non-determinism, it is not even proven to be a real thing, so it makes little sense to posit it as the source of quantum advantage. Non-locality is genuinely the only thing that fundamentally separates quantum mechanics from classical mechanics. Without non-locality, nothing about quantum mechanics would be spooky. Quantum computers perform computations on waves. The internal state of a quantum computer can always be represented as a single wave describing its wave function, independent of how many qubits the system has. When a logic gate is applied to any qubit in a quantum computer, the effect this has on the internal state of the quantum computer is as follows. First, the wave function is broken up into all the waves that compose it. Then, the amplitudes of each of these component waves are acquired. Those amplitudes are then rearranged to form a new set of amplitudes, and from this new set of amplitudes, they are then assigned back to the corresponding component waves. Finally, the updated state of the system is arrived at by combining these component waves. The exponential effects of non-locality can clearly be observed here. Why is non-locality the source of quantum advantage? Each component wave, eigenstate, that makes up the overall wave function is related to a basis state of one of a property of a particle, such as an electron's spin or a photon's polarization. These waves can all become entangled with each other to form the overall wave function of the computer. Applying a single operation to the overall wave thus can impact any of the amplitudes of component waves that make it up. Since each component wave corresponds to a possible basis state of a particle, this means affecting anything in the system can have a result of immediately impacting everything else. Every time another qubit is added, the number of possible eigenstates doubles, and so the complexity of the overall wave function grows exponentially. This also means that any operation applied to a quantum computer to manipulate its internal state also grows in complexity exponentially. This means that given a quantum computer of only a small number of qubits, it becomes infeasible for a classical computer to simulate how its internal state will evolve as logical operations are applied to it. This exponential increase in complexity does not sacrifice speed, due to the fact that applying a transformation to a single qubit can have an impact on every single one simultaneously and automatically, without having to compute iteratively the impact on all the other qubits.